So let's look at a derivation of the Laplace transform. Now we're going to think about the Laplace transform as an analogue of the power series. So we've seen the power series, which is written here whenever we looked at the Taylor series. So the power series is a sum of polynomials, so functions of the form a n x to the n. So you get a0, a1x, a2x squared, a3x cubed all the way up to a n x to the n. And we've seen when we looked at the Taylor series that we wanted to be able to approximate a function using a series of these simple polynomial functions. And we were able to do that by working out the values of the a0, a1, a2, a3, so on and so forth, and we're able to approximate a function a of x doing that. Now what we're going to say is that what we want to do is replace the discrete values of n with some continuous variable. So that variable we'll call t, and it's going to be any positive real number, so any number between 0 and infinity, any real number between 0 and infinity. So now the an is now the function a of t. The x to the power of n is now going to be x to the power of t. The summation will now be replaced with the integral from 0 to infinity with respect to dt. So now we're going to replace this power series here with a continuous analogue of it, and this analogue is going to be the integral from 0 to infinity of a of t, x to the t, and that's going to equal our value a of x. And our contention is that this is none other than the Laplace transform in a different guise. So we're going to go and work on this and get it into the usual form of the Laplace transform on the next slide. So we have our continuous analogue to the power series here, the integral from 0 to infinity of a of t, x to the t equals a x. Now we want the integral here to converge. So in order for it to converge, what we can do is we can restrict the domain of x to the values x is greater than 0 and less than 1. Now you can see here that if we had the value x was greater than 1, then you could have a function, say 3 to the power of t. And of course as t tends off to infinity, that's just going to get bigger and bigger, so the integral is never going to converge. Equally, if x was a negative number, then we would have run into the ideas of negative powers of possible say square roots. So that would mean that we would have a term here which would be a complex number or a complex function. So we don't want that either, so we want to keep that simple. So we'll restrict the domain from x is greater than 0 and less than 1. Now also what we want to do is we want to change the base here. We don't want it to be the base x, we're going to change it to the base e. Base e is much easier to work with, and it's much simpler in terms of calculus for differentiation and integration. So we want to change that base to e. Now in order to change the base, what we can do is we can write that function, that value x as x equals e to the ln x. E and ln x are inverses, so it means that these would cancel and this would just be a factor of x to the power of t. Okay, so we write this then, x equals e to the ln x to the power of t. So now we're interested in looking at the function ln x from those limits that we've set. X is greater than 0 and less than 1. So I've drawn it out here. We've got e to the x in blue here, and then the inverse is the ln x. And you can see the crossover points are 0, 1 and 1, 0. So we're interested in how does ln x behave between the points 0 and 1. And you can see that ln x is always negative between those 2 points. Now what we want to do is set it out so that this value is in fact a positive value. Okay, so rather than it running down like this, we'd much rather it ran down this way. Okay, so in order to do that, we'll just let the ln x equal a value of minus s, or equivalent we say s equals minus ln x. So now if we add all that up, we put it all back together, we're going to have an integral from 0 to infinity. Now we'll replace the function a of t with just some function f of t. So that would be f of t e to the ln x to the power of t by dt. Now, as I said, we replace this ln x with the value minus s. So we get the integral from 0 to infinity of f of t e to the minus st by dt. So that's none other than the Laplace transform. So the Laplace transform finally is f of s equals the integral from 0 to infinity over function f of t times e to the minus st by dt. Now that's the end of that derivation. It's not really one that I like the best. In the next video we'll look at another derivation, and that's my preferred derivation. So that's all there is for this video. I hope it was of use, and I'll get you in the next video. Goodbye.